Welcome back. We're going to continue our discussion of stoichiometry by looking at the limiting reaction of methane. Remember, stoichiometry is a discipline of chemistry that involves balancing equations determining the amount of reactants needed for a chemical reaction, or the amount of products made from a chemical reaction. Limiting reactions are those chemical reactions where there's a limited amount of a reactant, of one of the reactants. The amount of this reactant will determine how much products are produced. This is an important concept, particularly within the industry, where you have a certain amount of materials that you're using to manufacture, let's say a drug such as aspirin. You want to know how many pills of aspirin can you actually make. If you remember from our Big Mac example, this was a limiting reaction example. We had 18 hamburger patties, 16 hamburger buns, 3 whole tomatoes, a head of lettuce, a jar of pickles. Remember, there's about 10 whole pickles within a jar, a bottle of Thousand Island dressing, and a chunk of cheese. How many Big Macs can you make? I'll give you a moment to flip through your notes. If you recall, we have 16 Big Macs that can be made. Why? Because there are fewer hamburger buns than there are of any of the components to make up the Big Mac. The hamburger buns are the limiting reactant in this situation, the limiting ingredient. My focus today is using dimensional analysis to solve stoichiometry problems involving limiting reactants. In this lesson, we're going to apply what we've learned about using dimensional analysis and stoichiometry to solve the combustion of methane gas. This time, one of the reactants will be limiting. Recall that combustion reactions require 3 things: oxygen, fuel, and heat. In this case, our fuel is going to be a hydrocarbon, the hydrocarbon methane. And remember that methane is a hydrocarbon that contains 1 carbon atom and 4 hydrogen atoms. Now, if you consider the fact that we're doing this experiment on Earth, oxygen is in plentiful supply. Therefore, the methane is going to be the limiting reactant in this case. However, if I was to do this on the moon or on Mars, then oxygen would be the limiting reactant, possibly. We're going to start with the balance equation that we developed last time for the combustion of methane. Now, chemists use the unit mole when talking about the amounts of molecules. Within this lesson, I'm going to begin to use mole instead of atoms when I'm talking about this, or when I'm talking about the molecules. So if you look at my balance equation, I have 1 mole of methane, 2 moles of oxygen gas, 1 mole of carbon dioxide, and 2 moles of water. Now, a mole of methane is made of, interesting enough, 1 mole of carbon atoms and 4 moles of hydrogen atoms. 2 moles of oxygen gas is made of 2 moles of oxygen atoms. 1 mole of carbon dioxide is made of 1 mole of carbon atoms and 2 moles of oxygen atoms. Are you getting the idea? I hope you are. Recall that reactants are on the left side of the arrow. For methane, the reactants are methane, CH4, and the molecule oxygen, O2. Heat is always required for combustion reactions. And the products are written on the right side of the arrow. For combustions of any hydrocarbon, the products are always going to be carbon dioxide, CO2, and water, H2O. We will again use the what do I know method, writing down how many of each atom we have for both reactants and products. We're going to organize that information in our 2 by N table for both reactants and products. Again, N is going to be 3 because we have 3 atoms, carbon, hydrogen, and oxygen. And we're again going to cross-multiply our moles of molecules until we get a balance equation. For the balance equation, we have the following: 1 mole of carbon atoms in the reactants and 1 mole of carbon atoms in the products. 4 moles of hydrogen atoms in the reactants, 4 moles of hydrogen atoms in the products. 4 moles of oxygen atoms in the reactants, and 4 moles of oxygen atoms in the products. This is a balance equation. Now let's assume we have a small methane tank that contains 6 moles of methane. How much carbon dioxide will be produced if we use the entire tank of methane? We notice that we now have 6 moles of carbon atoms and 24 moles of hydrogen atoms. The moles of oxygen atoms has not changed. This is no longer a balanced equation, so we're going to have to rebalance our chemical equation to determine the answer of how much CO2 is going to be made. So let's start off as we did before with our carbon atoms. Now, carbon is only contained within methane for the reactants, and there are 6 moles of those. At the current time, we have 1 mole of carbon dioxide. And carbon dioxide is the only atom in the product side that contains carbons. The atoms are not balanced. Now, what would you do to balance the carbon atoms? I'll give you a moment. If you had 5 more carbon dioxides, in other words, say we have 6 moles of carbon dioxide on the products, then we have 6 carbons of reactants and 6 carbons of products. The carbon atoms are now balanced. But notice in doing so, we have changed the amount of oxygen atoms within this. We've gone from 4 oxygen atoms in the products to 14. Now, are you beginning to understand why I'm leaving oxygen to last? Now let's move on to the hydrogen atoms. We have 24 moles of hydrogen atoms on the reactants, but only 4 in the products. Hydrogen atoms are definitely not balanced. What would you do? If we multiply the amount of water molecules by 12 instead of 2, we will now have 24 moles of oxygen atoms on the products. 24 of the reactants, 24 in the products. The hydrogen and carbon atoms are now imbalanced. But you've noticed we've also changed the amount of oxygen atoms on the product side again. They've gone to 24. So now let's deal with the oxygen atoms. Oxygen atoms are not balanced because we have 2 reactants and 24 oxygen atoms on the products. What would you do? If we multiply the oxygen atoms by 12 instead of 2, in other words, say we have 12 moles of oxygen gas instead of 2 moles, then we'll have 24 moles of oxygen atoms on the reactants and 24 moles of oxygen atoms on the products. Now the oxygen atoms are balanced. Now, let's recheck our answers. We have 6 moles of carbon reactant atoms, and for the products, we also have 6 moles of carbon atoms. The carbon atoms are balanced. For the reactants, we have 24 moles of oxygen atoms, and 24 moles of oxygen atoms are also in the products. The oxygen atoms are balanced, and the hydrogen atoms are balanced as well. We see that we have a balanced chemical equation. And this gives us our answer. 6 moles of carbon dioxide will be made when we combust 6 moles of methane gas. Congratulations. You have both balanced combustion reaction involving methane and determined amount of product made in the limiting reaction. I bid you adieu. Until next time, take care.